Okay, looks like it's time for us to get started. So maybe just a couple of things to mention before we start. I have been making videos of these and posting them up on YouTube, so if there's ever a time you can't come to class, there will be a sort of a video backup. It's not as slick as lecture capture, but it's not the end of the world either, so it's kind of okay. The first assignment is open, so you should be working away on the first assignment now. To access that, you just go into Brightspace, click Assessments, and then Quizzes. You have unlimited tries, so keep at it until you get it right. If you need help, I'm always around, and the Physics Help Center is open Monday to Friday, and it's completely free. Just drop in and get help whenever you need it. Labs are starting in person this week, so Monday's group would have shown up this morning. Thursday's group should show up Thursday morning. Show up, do an activity, and you get graded. Any questions before we get going for today? Yeah?
Sorry, is your YouTube channel on the syllabus?
Yes. Wherever I list, might be up under my contact information.
Probably,
If you go YouTube and type Shoreland Physics, I should be your first hit, either me or my husband.
Yeah.
And there are links to these videos in the Brightspace as well. If you go under lecture notes, there are links here too. So hopefully you can find it. If you can't, let me know. So last day we talked about traveling waves. We looked at transverse, longitudinal. We looked at a description of the wave as a function of time, so any one spot on the wave. We looked at a description of the wave at any one, we looked at one position and one time. I should have an X in it, sorry. And where we're going to start today is with the combined expression. How do we get the full picture of the wave at any position and any time? So we're going to start putting those two together. So our goal is to find an expression for the wave, y as a function of x and t. So y of x and t equals 1. Let's start by thinking about a wave at t equals 0. So this is just one specific picture of the wave at time equals 0. So this is where the wave starts. Trace it out with a purple marker. So this is our wave at t equals 0. We know how to describe this wave. We've already written that down. So we can write down that equation. So the height of this string y as a function of x at t equals 0, so I'm going to plug in here 0 for my time. That's equal to the amplitude times the cosine of the wave number, or 2 pi over lambda, times x plus the phase constant. So there's an equation we wrote down last time. This picks one specific time, gives the height at every single value of x. Now what we have to think about is we know that our wave is moving. It has a wave speed v. We're going to restrict ourselves to talking about a wave moving to the right for right now. You can also do a left moving wave. I'm going to leave that for homework. So what happens to this wave over time? It moves to the right. So let's have a picture of what that looks like. So we know that our original wave is going to move to the right. Originally it was right here. I'll just trace that one out again. So here's my t equals 0, but now my wave is going to move to the right. It shifts over a bit. So this is some little bit of time bigger. T greater than 0. Okay, it moved right, not ground-breaking physics here. Now what we want to do is let's get an equation for this wave. So y, position x, time t is equal to what? Well, let's think about this wave. This green wave looks exactly like the purple one. It's just shifted ahead some small distance, right? It's just a little bit forward. So the green wave is exactly the same as the purple one. where the purple one is just a small amount of distance behind. You see that those two peaks are a little bit of distance apart, delta x. How far apart are they? Well, the wave is moving with speed v, so the distance apart they are is speed times time. Delta x is v times speed. So if we want the height of this wave, the general height of this wave, at some general position x, we know it's got the same form as this purple wave, wherever that was a little bit of distance behind. That little bit of distance behind would be x minus vt. Okay, there's the tricky concept here. Okay, and that negative sign tends to throw people. So is everybody good here? It says the green wave is the same as the purple one, which is a little bit before it. Okay, looks like we're good. So this wave is the same as y of x and 0 before, or behind, by an amount v times t. So if we want to write our equation, our general wave, the green one, is the old wave at a position of x minus vt. Okay, so all we have to do now is we want this purple wave, instead of at position x, we want it at x minus vt. So we'll just fill in x minus vt right here. A times cosine 2 pi over lambda x minus vt plus phi. So this is a sufficient way to describe that wave. It's not particularly nice looking, so let's just simplify it a little bit, and then we'll get a final form that we're going to work with all the time. So I'm going to multiply my 2 pi over lambda through. So a times cosine of 2 pi times x over lambda minus 2 pi over lambda times v times t plus phi. So I multiplied my 2 pi over lambda all the way through. Let's see if we recognize any of these terms. 2 pi over lambda, that's my wave number k. If we remember that v is equal to f times lambda, then v divided by lambda is the same as the frequency. And then we'll remember that 2 pi times the frequency is our angular velocity omega. So that's k, this is omega, there's our phase constant. So we're left with y of x and t is equal to a times cosine k times x minus omega times t plus phi. This is for a wave traveling to the right. Okay, any questions? If you go through this process for a wave moving to the left, and I suggest you do, I'll post solutions kind of step by step, but I think this is a good one for you to try. A wave moving to the left would be y of x and t is equal to a times cosine kx plus omega t plus phi. I'll just let people catch up with the notes, and then we'll do an example. Yeah.
So, besides just assuming that this is the natural direction we're going with the stuff we're talking about, like how would you know if a wave is actually like in motion versus just like a standing wave where we use like the original formulas or like equations we were talking about before?
So the chapter 14 stuff, if that's what you mean by the original equations,
Yeah.
that's for like a mass on a spring bouncing up and down. That describes the position of a mass as a function of time. This is different, right? This is not a mass on a string. This is an actual piece of string that moves with a wavy motion. So this is talking about the whole description of what the string looks like over time, not kind of where a mass on a spring is. It's kind of two different
So
things.
then that's where X comes in, because we're talking about it like moving.
Yeah, because the wave could be anywhere on the string. When we did the demo in class, I was at one end and we had a helper on the other end. And our equation says the wave everywhere between I was and the other student was. Okay, so not just a mass on a spring.
Okay.
So when you have problems, first of all, you're not going to be tested on chapter 14 because that was in 1050. You'll be talking about a sinusoidal wave. That's how you know it's these equations, not an object moving in simple harmonic motion.
Okay, sure.
Yeah, good to get all this stuff clarified right at the beginning. Okay, looks like we're all caught up. So now, let's do a multiple choice question. We have a wave on a string. It is traveling to the right. The green arrow shows the wave speed v. At this moment in time, so let's say this is playing on a simulation and I've hit pause. What is this little bit of string doing? We've got 5 choices. Is it going up or down? Is it going left or right? Or is it not moving at all? So kind of when I hit unpause, what's the motion going to look like? So I'm going to give you a moment to think about it, and then I'm going to ask you to commit to an answer. Feel free to talk about it with somebody sitting close to you if you want to kind of think it out loud through. Okay, so that's hopefully enough time to get a first set. So, of our choices, would anybody like to say what they think the answer is? Yeah? Up. So I got a vote for up. Who agrees? Do we have any disagreement? Okay, did you want to say what you think your answer is?
Yeah, I think it's 0.
Okay. So we got a 0. Anybody agree with 0? Okay, some agreement with 0. Anybody else want to pitch in with an answer? Down. So I got a down. Anybody agree with down? 2 little surreptitious nods. Okay, so what I kind of like about this question is it looks like a simple question, right? But so far we have 3 very different answers. So let's see if we can figure out what the answer is. I'm going to switch to a simulation. And I think these simulations are really kind of nifty. If you're home working on your homework, then by all means get these going and see if it helps you answer a question. You just Google PHET, P-H-E-T, and wave on a string. So I've got it set up. We're asking what happens to this green dot, because this green dot looks like the picture. So I'm going to hit play. It goes up. Okay, so the ups had it. All right. If this were a test question, I'm not going to let you whip out your phones and start a simulation to answer the question. So let's see if there was another way you could have figured that out. So for me, I know that the wave is moving to the right. Yeah?
The question says at the instant, what is happening to the dot? Not after the instant. So it's not supposed to be 0 because at that point it's on the rest line.
Okay.
This is after the instant, what happens to the dot?
Well, I see what you're saying, and I think maybe we're getting into a little bit of philosophical approach about word meanings. If we look at this, right, that green dot, as it passes through, it is moving, it's not still. And I did hit pause, that's true, because we have to print a picture at some point. But it's not still the way something is still when it turns around. It doesn't pass through a velocity equals 0. So it's moving up, 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 up. So even though I had hit pause, it wasn't truly stopped. Does that kind of make sense? Yeah, and that's kind of a good comment because you can go a little bit deep on these. It's probably why I don't ever ask multiple choice questions, because I think it's really easy to start wondering, well, what about this and what about that? I like explain questions, then you can get your reasoning across. So if this were on a question that you were trying to show me the answer for, since it's moving to the right, then a little bit of time before, it was a little bit to the left. So this is what our wave looked like before. So the little piece of string right there. Before I hit pause, the piece of string was down here. After I hit pause and it moves, it has moved to the right a bit. That would be this line. This is what the wave looks like after, and the piece of string right there is up here. So it goes from underneath the equilibrium to the equilibrium to up. So it is definitely moving up. Okay, make sense? Okay. So it can be a lot to these kind of simple questions. Okay, next let's move on to a typical sort of example. So we have that the vertical position of a traveling wave is described by this equation. And we want to answer a whole bunch of things about the equation. I think the best place to start with this kind of question, anytime you have something like that, is before we even look at what the question is, let's pause for a moment. Let's ask, what do we know right off the bat? So we have a traveling wave. We know that the general form of a traveling wave is y of x and t is equal to the amplitude times cosine of k times x, and it's either plus for a wave traveling left or minus for a wave traveling right, omega times t plus phi. Okay, so there's our general form. It's a good idea to start by writing this equation down. Just by comparison, when we look at this, we notice that we know a whole bunch of things. You can see that the amplitude is 0.75, k is 6.28, I've got a negative here, it tells me it's moving right, omega is 314, and phi is pi over 4. So just by thinking about the general form of the equation, I see right off the bat that I know a bunch of stuff. Okay, let's get into answering the questions. Is this wave moving to the left or to the right? Okay, I've already answered that question without even saying it so far. So we know that the wave is moving right because it has the form kx minus omega t. If it was kx plus omega t, that would be a left traveling wave. What is the amplitude of this wave? That's where our comparison comes in. The amplitude is 0.75 centimeters. Amplitudes do tend to be kind of small. They'll often be given in centimeters or millimeters. If you prefer to write it in meters with scientific notation, that's no problem. Either is fine. Okay, part C, what's the wave number, angular frequency, and phase constant? This one is also pretty straightforward. So K is 6.28. Even though I didn't write my units in right here, and some books will do that, they will leave the units out. That's why I did it this way, just to give you an idea of what that might look like. Typically, I will put the units in, especially on a test. Our wave number will have units of meter or radians per meter. If this were a test and you were really unsure, you could certainly ask for clarification, but typically I would put it in there, even though not all the books do. Angular frequency omega is 314 radians per second. Omega is not minus 314, it's positive, so omega is always a positive number. And our phase constant phi is pi over 4, and that would be in radians. Okay, writing down all these numbers with radians in them is probably a good idea to remember at this point. Your calculator is in radians mode. really common to get wrong answers here just because you've used degrees mode, yep.
Is phi always in that notation, or is it ever a decimal?
Oh, it could be a decimal.
Okay, cool.
I like the pi notation, books a
that's
lot
clean,
use
for
decimal,
sure.
yeah. Okay, part D, what's the wavelength in the period? So we can haul the wavelength and period out of K and omega. We have to remember those definitions. So part D, we know K is equal to 2 pi divided by lambda. That tells us lambda is 2 pi divided by K, 2 pi over 6.28 radians per meter. Gives us lambda equals 1.00 meters. So there's our wavelength. We'll do the same thing to find our period. We know omega is either 2 pi f or 2 pi divided by the period. That tells us our period is 2 pi divided by omega. 2 pi over 314 radians per second gives us a period of 0.0200 seconds. Okay, still good? Okay, next question, part E, what is the speed of this wave? I think I can get that in right over here. So we can use these numbers to help us find the speed. Two ways to find speed. We know that speed is frequency times wavelength. We've already calculated the wavelength. We could use our period to find the frequency, and we could do it this way. Or we could remember that speed is omega divided by K, 314 radians per second, divided by 6.28 radians per meter, to give us a wave speed of 50 meters per second. So there's our wave speed V. So that's kind of the pretty straightforward stuff. F and G is going to get a little bit more in depth. So at the position x equals 0, so the starting point of our wave, at what times is the wave at a maximum? So ultimately what we're going to shoot for is we know the wave is at a maximum. That means y is equal to the amplitude. We know x is equal to 0, and we're going to try and solve for t. So that's what we're going to do with part A. There's my equation, and there's the next slide. So I printed this slide this morning. I don't think I got that posted with your class notes, so I don't think that's in yours. Just because I did it last minute, realizing that I tend to plot everything and it can be a useful tool. So we'll talk about this as we go. So we're trying to figure out, at position x equals 0, at what time is our wave a maximum? Let's write that down as an equation. So part F, x equals 0, y equals the amplitude. We know that y at x equals 0 and time equals t is going to be the amplitude times the cosine of k times 0 minus omega times t plus 5. Okay, so right now I said I know my x equals 0, so I'm putting in x equals 0 right here. I'm writing my equation down in symbols just because I don't want to have to write it the numbers a bunch of times. If you were a numbers sort of person and you put all your numbers in here, no problem, that's fine. We know that y is equal to the amplitude, so let's put that in next. A equals a times cosine k times 0, 0, minus omega t plus 5. So if you wanted to graph it, you would put in Excel or whatever spreadsheet or your calculator, a times the cosine of omega t plus 5. If we look at the graph, we would see that that would go back and forth as a cosine, and it would be at a peak at some different times. So here are all the times it's at a peak. So these are all the places where y equals 0. These are all the times we're trying to find. And you wouldn't have to make this graph to solve the problem, but it can make it easier to visualize. So if you plotted this function, that's what this would look like, and you would know that you're trying to find these times. So let's go ahead and get to solving for these times. So this is going to be a reasonably straightforward solution. I'll divide both sides by a, so 1 equals cosine of minus omega t plus phi. To get rid of your cosine, you have to take the inverse cosine of both sides. Here's where it matters that your calculator is in radians mode. The inverse cosine of 1 is 0. And the inverse cosine of a cosine leaves us with just the argument. So you take the inverse cosine of both sides. The inverse cosine of 1 is 0. So 0 is equal to minus omega t plus phi. So minus omega t plus phi equals 0. T equals minus phi over minus omega. So minus pi over 4 radians divided by minus 314 radians per second. Put that through the calculator. What we get for an answer is 0.00250 seconds. So our calculator gives us an answer. We should put this answer in context. The wave is at an amplitude here. It is at a maximum. It's this tiny time. This is not the only time it's at a maximum because waves repeat sinusoidally. A period later, it will be back to a maximum. A period later, it'll be back again and again and again and so on. So we have to figure out a way we're going to write down all of those times because the question asks for all of the times, not the first time. So this is our very first time. Our next time would be T2, which would be T1 plus a period. And the period, remember, was 0.02. Our third time would be T3, which would be T2 plus a period. And so on. If we wanted to write that down, we would say all of the times, Tn, where n is which time we're talking about, it would be 0.00250 seconds plus n times the period, where n is equal to 0, 1, 2, and so on. So that gives us all of the times that the wave is at a maximum at x equals 0. Any questions? Yeah.
So that last section where we say Tn, like make the general formula there, is that what's going to give us like the completion of the question? Like is that what you're looking for?
Yeah, now part F is done.
Okay.
Yeah.
Cool.
Okay. It's really warm in this room. If anybody sitting up at the back wants to open up a window, please be my guest. They just pull open. But I recognize it's warm. You guys must be warm too. Okay. So the next part of the question, part G, says, at time t equals 0, what is the position of the first maximum and the first minimum? So this is a similar sort of question, but not exactly the same. This time we know t is 0, so when we have our equation, we can put in t is 0. We want to find the x value when we're at a maximum, that's y equals a, and we're at a minimum, that's y equals minus a. Okay, so that's our goal for part G. So I did a graph again because I always make graphs. And for this graph, I put in my equation for y and I plugged in t equals 0. So I said y of x and t equals 0 is my amplitude times the cosine of k times x minus omega times 0 plus phi. So I did this graph, I put in t equals 0, and this is what my graph looks like. It goes up and down. Here is my first maximum. Here is my first minimum. Here's where we might get into questions about what do we mean by first maximum and first minimum. We mean the first one after 0. Okay? So it's always kind of the first positive value. Did you have a question or just stretching? Okay. So these are the two values we're looking for. So we know that t equals 0. We know y equals a. We want to find what is the x value. Y equals minus a. What is the x value? And we know the wavelength in this problem is 1 meter. I'm going to write that down to get started. So let's start with what is x, where y equals the amplitude, and see what we get for our answer. So we'll put in y equals the amplitude equals a times cosine kx plus phi. And omega times 0 is just 0, so we leave that bit out. Divide both sides by the amplitude. 1 equals cosine kx plus phi. Take the inverse cosine of both sides. Kx plus phi equals the inverse cosine of 1, which is equal to 0 because your calculator's in radians mode. Still good? I know I'm going through this one really fast because we just talked all these same steps through in the previous bit. So if I want to solve for my x value, x is equal to minus phi divided by k, minus pi over 4 radians, divided by 6.28 radians per meter, gives me minus 0.125 meters. Now we need to take stock. This is a position where x is equal, where the height is equal to the amplitude, but this is a negative position, so this is before x equals 0. This is the answer our calculator told us. And it's true that the wave is at a maximum at that point, but this is not the answer to the question because we want the first value after x equals 0. So we've got two options right here to solve this problem. Kind of depends on how you think about cosine and how you think about math. You might think, well, when I do cosine, inverse cosine of 1 to get 0, that's true, but that's not the only answer. Inverse cosine of 1 could also be equal to 2 pi. Could be 4 pi, right? We got a bunch of answers here. So we could think about that, and we could put in different answers here and solve for our x. Or, and here's where the picture of the graph is really kind of helpful. I know if I have an amplitude here, I know one wavelength later I'm going to have another amplitude. So I know those two crests are separated by a wavelength. So this value of x, the one that I'm trying to find, is this value plus the wavelength. That's probably the most straightforward way to get to our answer here. So let's do it that way. So the x value that I want, x of the first maximum, is going to be the number I just found on my calculator, plus a wavelength, which is 1 meter. So that gives me 0.875 meters. There's the location of my first maximum. The next part of the question, find the first minimum. That's this value. Again, you could go back to your starting equation. At the minimum, you'd have minus a in right here, and you'd be solving for an x value. That would be perfectly appropriate, and you could get your answer that way. But there's a faster way. Every maximum and minimum is separated by a half of a wavelength. So this is a real quick way to get the answer. So between here and here is lambda over 2. So for our first minimum, it's going to be minus 0.125 meters plus lambda over 2. That would give us 0.375 meters. Any questions? Yeah?
Would the number be different if the wave travels to the left?
Oh, what a good question. So the question was, would it be different if the wave was traveling to the left? We'd apply the same sort of physics, but we would certainly get different answers. Yeah, good question. Oh, maybe I'll put that one on the test. Okay, so now let's get ready to move on a bit. So the next thing in your notes, if you've printed them off or you've got them open on a PDF viewer, is a homework example. I've got a video solution done for this. I'll post that video link with the lecture notes as well as a written solution to this. So here's something you can try for a little bit of extra practice. And that brings us to here. So we're going to return to the idea of a motion of the wave coupled with the motion of the elements of the medium. So a wave is a disturbance that travels down a medium like a rope or a slinky, and it moves because the elements of the medium, they interact with each other and they also move. So our wave, our disturbance, that moves with what we call the wave speed, which has a symbol of v. That's equal to f times lambda, or omega over k. For the purposes of this class, but not the entire universe, this wave speed is constant. The reason we have this wave is because we have a source oscillating up and down with simple harmonic motion. It makes our medium oscillate up and down with simple harmonic motion. That's why we call it a sinusoidal wave. So every little piece of this string moves up and down with simple harmonic motion. And those bits of wave interact and they propagate the wave along. Every single element has its own speed. So notice the difference in the nature of the motion. This is a bump going down a line with constant velocity. This is a little bit of string moving up and down with simple harmonic motion. So each element has what we call transverse velocity. That has a symbol that we call v with a subscript of y. Because it's moving with simple harmonic motion, it goes as a sine or cosine. It means it's not constant. So when you're asked to find the speed of a wave, so if the question is find the speed of the wave, that means wave speed and you do this. If you're asked to find the transverse velocity or the velocity of an element of the medium, that means find this. So be careful with that nomenclature. You don't want to get those two mixed up. So let's switch to how we're going to figure out that transverse velocity. Yeah.
Sorry, can you say again why it's not constant?
Because it's moving up and down with simple harmonic motion. That means it goes as a sine or a cosine.
Right.
Yeah, so sine and cosine vary.
Right, acceleration changes on the way.
Yeah.
True.
So, to find that transverse velocity, let's start with the fact that we know the equation for the position of every bit of that string for all of space and all of time. There's our equation for position. If we want to get the velocity, we have to take the derivative. Okay, so if we have the position equation, to get the velocity equation, you take the derivative. So let's get started on that derivative. First of all, maybe I'll point out that I'm going to go through the analysis for a wave moving to the right. Okay? And we're doing transverse velocity. As a homework project, you can work through waves moving to the left, okay? Just to make sure you kind of get it. So if we want to find the transverse velocity, we know that velocity, which will be a function of position and time, is going to be the derivative of the position with respect to time. This notation, who's seen this before? Some, not everybody. This is called a partial derivative. I cannot remember what math class you see that in. A partial derivative is a lot like a regular derivative, but you write a partial derivative when you only care about the change with respect to time. It means we're going to take the derivative of this equation, we're going to take it with t as the variable, we take everything else constant. Okay? So everything is constant except time. And it's got a special symbol. They're like little curly D's. They call them die, which sounds really aggressive, but that's what they call it. So you would say die y, die t. So let's put our equation in and start to take that derivative. Die by die t of a times cosine kx minus omega t plus phi. First thing we can do, just like any derivative, we can take our constant out front, so amplitude comes right to the front. So a die by die t of cosine kx minus omega t plus phi. Next, we want to take the derivative of cosine. The derivative of cosine is negative sine. So we get a times minus sine. We've got exactly the same argument, kx minus omega t plus phi. Then we have to apply the chain rule, which says we have to multiply by the derivative of the argument. Just assuming most people are comfortable with derivatives and chain rule and stuff. If you're a little shaky on that and you want to talk to me afterwards, no problem. We'll go through some examples. So this part right here, here's where the partial derivative bit is really important. We'll have to take the derivative of each bit, derivative of kx minus omega and phi. The derivative with respect to time of kx is 0, because k is a constant, and we're treating x as constant because time is our only variable. So this equals 0. The derivative of minus omega t is minus omega. And the derivative of phi is 0, because that's a constant as well. So that whole bit is just minus omega. So I've got a times minus sine kx minus omega t plus phi times minus omega. Simplify it all down. So our v expression is a, I've got minus times minus, that gives us a positive. And bring my omega to the front. So I've got plus a times omega times sine kx minus omega t plus phi. So there's the equation for the velocity of every little bit of string as it moves up and down for all of the positions and all of the times.
Is that a T or a plus in front of A?
That's a plus. So we'll just say that's positive. So when we talked about, let's see, when we did our review of simple harmonic motion, we looked at what was the maximum velocity in simple harmonic motion by thinking about the two ranges of sine. We can do the same thing with a traveling wave on a string. If we know that this is our equation for the transverse velocity of the medium, if we wanted to find the maximum value, we just think about what happens to sine. So we know that sine has a range between plus and minus 1. So to get a maximum transverse velocity, we would have that our sine value, sine kx minus omega t plus phi, that would be equal to 1. And then our transverse velocity would be a times omega plus 1, or a times omega times 1, so just a times omega. Okay, questions? Okay, so there's our velocity. We can also do acceleration. To get our acceleration, we're going to take our velocity equation and take the derivative with respect to time.
If we were to do a V Y max, would that just be a negative a omega?
No, you lost me when you said if we do Vy max, because this is Vy max. Minimum? Oh, see, then we're getting into velocity again. So I would probably argue that the minimum velocity was minus a omega. Some people would argue that a minimum velocity is 0. For my part, if I ever ask you this kind of question, I'll try and be super specific which I'm talking about. But yeah, -1 would give you negative A omega here. It's the other range. Okay, so now for our acceleration equation, we're just going to take the velocity equation, take the derivative, it's going to give us acceleration. So our transverse acceleration as a function of position and time is going to be the partial derivative with respect to time, A omega sine kx minus omega t plus phi. So A and omega come out front. The derivative of sine is positive cosine. And then we also have to multiply, use our chain rule, so multiply by the derivative of kx minus omega t plus phi, which we saw in the last step was just minus omega. So there's my derivative done in all one step there. That gives me that my transverse acceleration is minus a times omega squared times cosine kx minus omega t plus phi. So there's the transverse acceleration. Two things to notice about our transverse acceleration. So item number 1 is that our maximum transverse acceleration is what we would get if cosine of kx minus omega t plus phi was equal to -1. So our maximum acceleration is going to be a times omega squared. And then the second thing we would notice, if I pull my omega squared out front, I would find my equation of y again. So y is a times cosine kx minus omega t plus phi. So my acceleration, just like in simple harmonic motion, is equal to minus omega squared times my position function. Okay, so it has a similar behavior to what it had in simple harmonic motion. Questions? Okay, so this was all, yeah?
So A1 max is positive A squared because it'd be like the inverse cos of -1 to
It's-
get.
Because the smallest value cosine can ever have is -1. We put in -1 here, we get minus a omega squared times -1.
Right.
That gives us
Okay.
a omega
I
squared.
get you.
Okay, so for a homework, I'm going to say work through this for a left moving wave. See what the equations are. Spoiler, the equations are not going to be the same. So you have to make sure you really understand left versus right. And then the last thing, I have to run to another class in a different building today, so I don't have time to stop after class for questions today. But if you have any questions, please email me or drop by my office this afternoon. I'll be around pretty much all day.